Okay, so this is scenario 2. A researcher conducted a study to investigate whether local car dealers tend to charge women more than men for the same car model. Using information from the county's tax collection records, the researcher randomly selected one man and one woman from among every one who had purchased the same model of an identically equipped car from the same dealer. The purchase process was repeated for a total of 8 randomly selected car models. Summary statistics are also shown below. First off, I want to address the summary statistics. Whenever you have to input data, or almost always, you can expect them to give College Board to give you a mean and standard deviation. And basically the reason they're doing this is so that you can check to see that you actually input the data correctly. So I should have been able to put the women, let's say, into L1, and then do a stats bar and go, yep, I got an average of this, a standard deviation of that. I'm very confident that I input my data correctly. You should have been able to put this into L2 and sit there and do the exact same thing, a stats var, check L2, and see that I got this mean and this standard deviation. Once again, they do this regardless whether this is a paired test or a 2-sample test. So please always know that you use those things to check your work. They may or may not be part of the problem. In this case, they weren't part of the problem because this was a paired test, all right? And the reason I know this was a paired test is because I had car models, and I had a man and a woman who purchased car model 1, a man and a woman who purchased car model 2. So I had a pairing based on the car, okay? I don't know, I mean, so this would have been a paired test. Now, normally, or in previous years, we have given this as a actual test question. And the difficulty students run into is they're like, gosh, do I run this as a paired or do I run this as a 2-sample? First off, we know the data links are the same. So that does not eliminate the idea that it's paired. If the data links are different, then you know it can't be a paired. All right, that makes it easy. That part's easy. But could this have been run as a 2-sample? And the answer is yes, it could have. But we know that for every car, we had a testing with a woman and a testing of a man, a testing of a woman and a testing of a man. So we had two, basically, it was tested twice. When something is tested twice, it's paired. The other thing is, generally speaking, if we can run a paired test, we should, because it controls for all sorts of differences. All right, it controls for all sorts of differences. So had you messed up and ran this as a 2-sample T as opposed to a paired, and I know at this time you didn't know how, but if this were on the test and you ran this as a 2-sample T as opposed to a paired, you drop from full credit to half credit immediately. If you run the 2-sample correctly, you get half your credit. Now, that sounds horrible because you're like, I went from 100 to a 50. Remember, with the curve, that 50 actually ends up being a passing score of a 70. So basically, you can still make a 3 on the exam or a 70 in the class, but that's not what we want. We want to try to get that 5, and we want to try to get that A on the test. So this is a paired test because each one was tested twice. Before I go any farther, I'm going to let Ms. Lamb see if she wants to add anything to that. So resuming recording, does the data provide convincing evidence that on average, women pay more than men in the county for the same car model? So here we go. Null hypothesis. Since I'm testing twice, this is going to be mu d equals 0. It is going to be a very, very rare situation that is anything but a 0. And I don't think they've ever done that for AP statistics, so I really wouldn't worry about it. The alternative, mu d and 0, we have this part, but here's where we have to be careful and take a moment and decide which way you're going. Well, because they listed women first, I'm going to go women minus men. That just happened to be the order that they went in. L1, L2, because that's where I'm going to input my data. Now I'm just going to choose a price for women. And I'm just going to say the price was $10. But they said they want to pay women pay more. So this is going to be some value less than that. Let's just say it was $8. So when 10 is greater than 8, that lets me know the direction. All right. Because if you'd gone the other way, men minus women, you're going to need to flip it. And let's just say you've done men minus women. That's not wrong. If you had done men minus women, you say, well, the women paid $10, the men paid $8, and then you would have to change your inequality. So take a moment and do that every single time. All right, that way when you go to define it, everything makes sense and your inequality is in the right spot. So let mu d equal the true population mean difference in car price. Absolutely have to have this. What order? Well, I'm going to do women minus men. Why? Women came first. All right. So I took a moment. I entered all that data into L1 and L2 because I'm going to need to do that. Conditions. So what are my first conditions? First off, random sample given. Two, we need to check the 10% condition. Honestly, I have a little bit of issue on this one, but 8 divided by 0.1 equals 80. Reasonable to assume that there were at least 80 car model purchases. The sample is less than 10% of the population. The next condition is one that was not on the one sample, and that's independence of the differences. So reasonable to assume that the differences are independent. One purchase difference should not have impacted another. And if it truly is a random sample, it should not have. In other words, should not have impacted another. And here's why. If it's a random sample, the fact that I purchased and another woman purchased in one vehicle and then someone else purchased another one, prices shouldn't have an impact one versus the other. Not a random sample, very easily could have happened. Step 4, or condition 4, normality. Small sample size cannot be normal by central limit theorem. It would have been really nice if they told me the underlying distribution is normal. If they told me the underlying distribution is normal, I could say the underlying distribution is normal. We're good to go. We're satisfied. They didn't. So I need to take a moment and I need to do a stat plot. I need to do a box plot. To do that, I had to input the data in L1 and L2, but I don't want a plot of L1 and a plot of L2. I need a plot of the differences. So that means I'm going to go second 1 minus second 2, and it populated that for me. Then I'm going to go second stat plot, press enter, arrow to the left, make sure it's turned on, drop down and select, make sure you're selecting the box plot that has the outliers. My list is an L3, so second 3. Press enter, my frequency should be 1, press zoom 9. So I got this box plot, and I just always take a moment, I just sketch it sort of the way I interpret it looking. Now, you can draw a scale if you're really good. I'm not that good, so I don't draw a scale. What I end up doing is I label the major points. The first major point was -100. The next major point ended up being 95. The next major point was 595, 1050. This is where I really need my glasses, and this is 1300. I need to label this. All right. So what is this graph of? My graph is the difference in model price and I'm going to abbreviate for this, but please don't. W minus M, women minus men. That right there is not enough determination. It's really nice that I drew that box plot. Everyone's going, oh, they drew a box plot. What does it mean? Well, the box plot is reasonably symmetric with no outliers. The distribution appears to be, and I'm going to abbreviate, approximately normal. Notice I said the distribution appears to be approximately normal, not the distribution of the means. Why? I don't know what the distribution of the means may or may not be normal because our sample size isn't large enough. We can only talk about distribution of means if our sample size is 30 or larger. So here we're saying the distribution because we're talking about, hey, you know what? This is our sample. We know that samples should look like the population. So the distribution of the sample is approximately normal. Therefore, we believe the distribution of the population is approximately normal. That's essentially what we're saying, but we can shorten it down to just saying the distribution appears to be approximately normal because we know samples should look like the population. Okay? All right. My equation. X bar D minus mu D SD divided by square root of N. Well, I need to get that from the calculator. So I can get that from the calculator by going stats, excuse me, second bars. I did it wrong, excuse me. Stats, calc, one variable stats. My list that I'm interested in is not L1, it's L3. And I end up getting X bar D equals 585. SD equals 530.71. We know my sample size is 8 and my degrees of freedom happens to be 8 minus 1, or 7. If I'm drawing a graph of this, my claim is mu d is 0. So we have an x bar d that's somewhere up here, and our x bar d is 585. So we want to know how likely it is that we would get an x bar d that was greater than or equal to 585 if this were actually true. So that is the probability that t is greater than, or 585 minus 0 over 530 divided by the square root of 8. And what does that yield? Stats test, t-test. Make sure data is highlighted. Now I need to put in my mean. My mean was what the null hypothesis was, which was 0. My list of data was in L3. This needs to be greater than 0. And I calculate. So the probability that t is greater than 3.1177 equals 0.0084. They told us to test at an alpha of 0.01. So this is my p-value. Here's my alpha, 0.01, make them the same length. Well, 84 is definitely less than 100. So this is less than. So our decision is reject the null. And by the way, just telling me to reject is not enough information because I don't know what you're rejecting. If you just say reject or fail to reject, that's not good enough. You need to say reject the null or reject HO or fail to reject, or fail to reject HO. You have to say what it is you're rejecting. And it just needs to be one word. So our P value is 0.0084. We reject the null. There is sufficient evidence at alpha equal 0.01 to suggest that the true population mean difference in car price, women minus men, is greater than 0. Simplified statement. On average, women pay more than men for the same car model. So on average, our study says we reject the null, and what that means is on average, women pay more than men for the same car model. We have not been pushing the simplified terminology yet, but that is going to be something we start pushing very hard in our next, as we go into our next set of tests, which is proportions. And when we get to preparing for the AP exam, we're going to be pushing the simplified definition very, very hard, because that shows that you actually understand what it is you did. You just didn't just repeat our template.